Science 460, Application Architectures. This is Chapter 28 from the web. We've covered a bit about application architectures in Chapter 6, but here we're going to take a closer look at these. So this is a very old thing that I found on the web as an example architecture. Gosh, it's been many years ago. And it was too priceless not to keep here. We're going to try to come up with something that's a little bit more descriptive for you and ways to describe these that you can find as better ways. Here's a far more professional one, and this is what a real application architecture might look like. So here we have the presentation tier, the business tier, and the data tier, and you can see how the database ties to the different parts of the organization: company, resource allocation, contract, document, and contract. So you can see how each tier ties to each part of the business. So, that's a real application architecture versus the very colorful Mondrian one that we saw on the last slide. So, usually systems of the same type have similar architectures, but they do differ in the type of functionality that they provide, and that's what we mean when we talked about vertical markets. And basically, we can use the same architecture over and over again to provide similar functionality, similar systems that provide slightly different functionality. We can reuse the application architecture. So Chapter 28 looks at generic structural models for several different types of application. And data processing applications are applications that are data-driven. They process data in batches without explicit user interventions during the processing. The specific actions taken by the application depend on the data that it's processing. Batch processing systems are commonly used in business applications where similar operations are carried out on large amounts of data. They handle a wide range of administrative functions such as payroll, billing, accounting, publicity. So you can imagine a data processing system might handle, producing all the paychecks for the state of Hawaii. Or reconciling all the accounts at a major bank. Transaction processing applications are database-centered, and they process user requests for information and update the information in the database. These are the most common type of interactive business systems. So when you go and look for a flight on Hawaiian Airlines, they'll query their database to see what seats are available on that particular flight if you've selected that particular flight. They're organized in such a way that user actions can't interfere with each other and the integrity of the database is maintained. The class of system includes interactive banking systems, e-commerce systems, information systems, and booking systems, as I just mentioned. Event processing systems is a really large class of applications where the action of the system depends on interpreting events in the system's environment. The events might be the input of a command by the system user or a change in variables that are monitored by the system. Many PC-based applications, for example, video games, editing systems such as word processors or Google Docs are event processing systems. Image editors and presentation systems like the slides that you're looking at now are also event processing systems. And real-time systems, which we'll talk about in Chapter 21, also fall into this category. And last but not least, one of our favorites is language processing systems. This is where the user's intentions are expressed in some sort of formal language. For example, Java or Verilog or VHDL or C++ or C#. Language processing systems process this into an internal format and then interpret the internal representation. The best known language processing systems are, of course, compilers, which translate high-level language programs into machine code. However, language processing systems are also used to interpret command languages for databases and information systems and markup languages such as XML. So, there are several ways to use generic structures that we can have for these application architectures, and you can use them as a starting point for the design process, as a checklist for things that you should have in your architecture, a way of organizing the work, as a work breakdown structure, which is one of the things we do with our Kanban boards, our Gantt charts, and PERT charts. As a means of assessing components for reuse, hey, we've got this previous application architecture. What are the things that we can reuse from that previous application architecture? Or as a vocabulary for talking about types of applications. And in terms of means of assessing components for reuse, there's that old saying, good writers borrow and great writers steal, from Ted Berrigan. And I've probably covered Ted Berrigan at some point, but it's worth covering again along with the source material. And I've got this little note here from Ted Berrigan's Poetics of Appropriation by Reva Wolf. A notable example is the crooked and sloppy way either he or Joe Brainerd pasted a photo booth picture of Berrigan on top of and covering over a picture of the founder of visual appropriation, Marcel Duchamp, in a 1965 remake of Duchamp's 1923 wanted $2,000 reward in literary magazine Culture. Here he appropriates the persona of Duchamp in The Appropriator, but in a decidedly clownish way. He holds a finger over each ear as if to hear no evil. The evil being, we can guess, the act of stealing that appropriation entails, as well as the crime for which Duchamp and later Berrigan presumably is wanted. The inclusion of Berrigan's mug in the wanted poster contains artistic and literary as well as real-life associations. He did steal. Books mainly, as he mentioned in several of his journals. For example, in late July or early August in 1963, went to steal books today, got $10 worth. And what Berrigan would do is he would steal the books from bookstores that his friends had written, had his friends sign them, and then sell them back as signed copies. The quote is from Ron Padgett. Ted and I used to steal books, but we never felt guilty about it. I think we assumed we had a right to those books, the way a starving man feels about stealing food. The first few years in New York, neither of us had any money. Well, let's move on to data processing systems. So data processing systems are another class of application architecture, and these are ones that are data-driven. We process data in batches without explicit user interventions, and they're good, as we mentioned before when we did the overview, for handling a large amount of operations on similar data, payroll, billing, inventory, etc. Somerville also, for some reason, lists publicity. I'm not sure why. Any idea? I don't know if people are generating publicity on a nightly basis, but that may be the case. And it's worth noting that this chapter did predate the advent of social media, but I don't really think you want to handle social media in the same way as you handle payroll or billing, unless you were rolling things out at a certain time. I think people just tweet whenever they feel like they have something to say. So components of data processing systems. One is the input component, which reads the data, checks its validity, does some correction of errors, and then the processing component, which takes transactions from a queue, performs computation on the data, and creates or updates the data records. And then the output component reads the records from a queue, formats them, and then sends them to an output device. So, we can think of this as outputting the results of nightly inventory into a PDF report. So the general architectural model for this has three components: input, process, and output. And this is what you did in your procedural program. Input component reads types of data from the input files or from a database, checks the validity of that data, and corrects some errors. Then queues the valid data for processing. A processing component takes a transaction from a queue, performs some computations on the data, creates a new data record indicating the results of the computation, the process, and then queues this new record for printing. Sometimes the processing is done within the system database, and sometimes it's a separate program that interacts with the database. An output component may read records from a queue, format these according to the output process, and then send them to a printer or to a PDF file, which is more common nowadays, and then write the new records back to the database. This figure shows how data flow diagrams can be used to show a more detailed view of the architecture of a data processing system. This figure shows the design of a salary payment system. In this system, information about employees in the organization is read into the system. Monthly salary and deductions are computed. So, you have your things like your taxes, your health insurance, your dental insurance, retirement savings, etc. And then the payments are made. You can see how the system follows the basic process output structure. Transformations are the rounded rectangles, and arrows indicate data processed by the function. Files or data are represented by the square boxes. And apologies for the very old image of this. I don't think Somerville has updated a lot of the diagrams here. So let's move on to transaction processing systems. These are database-centered applications. They process user requests for information and update the information in database. The most common type are with interactive business systems, e-commerce, booking systems, and they're designed to process user requests from a database or update databases. Technically, a database transaction is a sequence of operations that's treated as a single atomic unit. All the operations in a transaction have to be completed before the database changes are made permanent. This means that a failure of operations within the transaction doesn't lead to inconsistencies or false commits to the database. So any coherent sequence of operations that satisfies a goal is a transaction. For example, with an ATM withdrawal, you get details of the account, check the balance to see if it's there, modify the balance to deduct the amount of money taken out, and dispense the cash. And changes are not made until everything is successfully completed. And here we have a picture of Khmer Rouge money. The Khmer Rouge famously abolished money after declaring the year zero, but the Chinese actually made them print notes in order to pay for weapons that they were buying from the Chinese. So a little bit of Southeast Asian history there. Batch processing systems, these are old school transaction processing systems. And again, it goes to that thing that we learned in CS 150, input, process, and output. They're now more interactive and include updates one at a time, but generally they process things in batches, so in groups, like reconciling the inventory on a daily basis. So you have your input-output processing, application logic, transaction manager, and database included in the batch processing system. So here's an example of an application transaction processing system in the form of a banking system allows customers to query their accounts and withdraw cash from an ATM. The system is composed of two cooperating software subsystems: the ATM software and the account processing software in the bank's database server. The input and output subsystems are implemented as software in the ATM, whereas the processing subsystem is in the bank's database server. So this shows the architecture of this, and he's added some detail of the basic input-output diagram to show components that may be involved in these particular activities. I've deliberately not suggested how these internal components interact, as the sequence of operation may differ from one machine to the other, is what he stated. And it's 2019, 2020, actually, and he's never updated the blue bounding boxes, and I guess I'll say, oh, well, it's a free chapter. So, in systems such as bank customer or accounting systems, there may be different ways to interact with the system. Many customers will interact through ATMs, but bank staff may use counter terminals to access the system. There may be several types of different ATMs. There may be several different types of ATMs and counter terminals used, and some customers and staff may access the data through web browsers. To simplify the management of different terminal communication protocols, large-scale transaction systems need to include middleware that communicates with all the different types of terminals, organizes and serializes the data from the terminals, and sends that data for processing. This middleware is sometimes called a teleprocessing monitor or a transaction management system. And IBM CICS is a very widely used example of such a system. So information and resource management systems, they allow controlled access to a large base of information. Large examples, library catalog, flight timetable, or patient records. And you can use a layered model for these. Somerville explores the library model as an example. And all systems that involve interaction with a shared database can be considered to be transaction-based information systems. An information system allows controlled access to a large base of information such as hospital, library catalog, flight timetable, or records of a patient in a hospital. Development of the World Wide Web means that a huge number of these information systems move from being controlled by a specialist in the organization to being universally accessible for general purpose systems. And that's been a grand challenge over the past 20 years or so, is moving these online, but we've successfully done that to a large extent. The layered model, which you may be familiar with from OSI, is a very general model of an information system. The system is modeled using a layered application approach. The top layer supports the user interface. The middle layer supports communication. The third layer supports information retrieval and modification. And the last layer promotes the transaction management with the database. And what's nice about these is if you modify one layer, it only impacts that layer and its communication. So if we modified the user interface, it wouldn't modify the communication between the information retrieval and modification and the transaction management database layers. So an example of this is Somerville's library information system. Here you can see how this particular system maps to a layered model from the previous slide. He pretty much ditched this library system everywhere but the web chapters for the 10th edition, but it still makes a good example of where you could use a layered application architecture. Resource allocations are also transaction processing systems. So some basic architecture is included, or the same basic architecture is included in them. Examples are timetable systems, such as allocating classes to time slots, library systems, and air traffic management systems. And by the way, I'll just point out that scheduling systems tend to be NP complete and somewhat equivalent to bin packing at the optimal level. Good heuristics can ensure a decent solution, but you're probably not going to get the optimal assignment of teachers to classrooms or teachers to classes. So what are the components of a resource allocation system? Resource database, a rule set for assigning things, resource management component, allocation component, authentication module, query management module, resource delivery component, and user interface component. And we can try to map these to the four-layer model. E-commerce systems are also a type of resource allocation system. So if we want to map these to a layered model, here's what it would look like for the 4 layers. And again, apologies for the older figures here. For the e-commerce system, here's how we could map these to the 4 layers for the e-commerce system with web browser, web server, application server, and database server. And these are usually organized as multi-tier architecture with the application layers associated with each tier. So moving on to event processing systems. Basically, these are a large class of applications. Actions of the system depend. Actions of the system depend on interpreting events in the system's environment. So, for example, games, what happens when you press the A or the diamond button? How does the system respond to that? Word processors, GUIs, and real-time systems. General challenges with these are the timing of events is somewhat unpredictable, and the system needs to cope with them when they occur rather than queuing them. I mean, there is some queuing that's necessary if you do 2 actions at once, but you need to process those rather quickly. So an example of these are editing systems, and these are the focus of Somerville's examples, although games are certainly a application of this type of application architecture. Key characteristics of editing systems are mostly single user, although nowadays with things like Google Doc, we have multiple users. They need to provide rapid feedback so you can see the edits that you've made, and they have much longer sessions than for ordering goods unless something goes terribly wrong with the ordering goods. So the architectural components are the screen. This object monitors the screen memory segment and depicts events that occur. Events are passed to the event processing object along with the screen coordinates. Event is triggered by an event arriving to the screen. It uses knowledge of what is displayed to interpret this event and to translate this into the appropriate editing command. So did we select something, or move our mouse over something, or right click on it? This command is then passed to the object responsible for command interpretation. For very common events such as mouse clicks or key presses, the event object can communicate directly with the data structure. This allows for faster updates of that structure. A command that's usually, this object processes a command from the event object and calls the appropriate method in the data editor to execute the command. And then the editor data, when the appropriate command method in the editor data object is called, it updates the data structure and calls the update method in display to display the modified data. Ancillary data, as well as the data structure itself, editors manage other data such as styles and preferences. In this simple architectural model, this is bundled together under ancillary data. Some editor commands, such as a command to initiate a spelling check, are also implemented by this method. And file system, this object handles the opening and saving of files. You do want to frequently save if you're editing a file. This can either be editor data or ancillary data. To avoid loss of data, as many editors have autosave facilities that save the data structure automatically. They can be retrieved in the event of a system failure. And lastly, display. This keeps track of the organization of the screen display. Calls the refresh method in the screen when the display has changed. Moving on to language processing systems. These accept a natural or artificial language as input and generate some other representation as an output. Examples are compilers, XML, and translation services, such as the one that was used for zeroing. How are you, gentlemen? Wow, it's been since 2001 already. Probably Zero Wing's a bit before your time, but it's still worth checking out. Those were indeed good times, and Katz is still a hero to many. So, at the most abstract level, the architecture of a language processing system is illustrated here. The instructions describe what we need to do, and these are translated into some internal format by a translator. These instructions correspond to machine language of the abstract machine. These instructions are then interpreted by another component that fetches the instructions for executions and executes them using data from the environment. The output of the process is the result of interpreting these instructions on the input data. Of course, for many compilers, the interpreter is a hardware unit that processes machine instructions, and the abstract machine is the real processor. However, for many languages such as Java, the interpreter is a software component, which is why Java sometimes runs a tad bit slow. So, in looking at an overview of a compiler, you have your lexical analyzer that takes input tokens and converts them to an internal form. You have a symbol table, which holds the information about the names of the entities, variables, class names, object names used in the text that is being translated. A syntax analyzer, which checks the syntax of the language being translated. It uses a defined grammar of the language, and it builds your syntax tree. The syntax tree is an internal structure representing the program being compiled. Semantic analyzer uses information from the syntax tree and the symbol table to check the semantic correctness of the input text language. And a code generator that walks the syntax tree and generates abstract machine code. Lots of components. You can also have a repository modeler of a compiler, which has evolved a little bit from the data flow model. This figure illustrates how the language processing system can be part of a set of integrated programming support tools. In this example, the symbol table and the syntax tree act as a central information repository. Tools or tool fragments communicate through it. Other information sometimes embedded in tools such as grammar definition of the output format for the program have been taken out of the tools and put in the repository. So a syntax-directed editor can check the syntax of a program as being correct while it's being typed, and the Pretty Printer can create listings of the program in a format that's easy to read. And again, the blue is still there, but he did fix the kerning for the 10th edition, and this looks a lot better than the 9th edition. So I think that's all for now. It's a longer lecture than I usually give, but thanks for listening all the way through. Appreciate your time.